Okay. Keith, do you want to start us off?
Okay, would you like me to introduce Christian, Colleen?
I do. That would be great.
Okay. All right, thanks everybody for coming. It's my pleasure to introduce Christian Woods. Before joining Rutgers, Christian earned a bachelor's degree in mathematics as well as a bachelor's degree in computer science, both from the University of Pittsburgh. And he earned a master's degree in mathematics from the University of California, San Diego. Between that time and joining us, he worked in industry programming educational software for mathematics education. When Christian came to Rutgers, he was awarded a presidential fellowship and has done wonderful work in his dissertation, as well as for our research team. One particular area in which we've greatly benefited from working with Christian is with our work in designing proof comprehension assessments. So in this work, this required interpreting the subtle meanings of students' responses to our assessment questions. And doing this well required a deep understanding of advanced mathematics and a capacity to attend to carefully to students' subtle comments. And these are skills in Christian's wheelhouse, and he's one of the best collaborators that we've had in doing this type of analysis. In this talk, Christian is giving a talk from his first year research project. And the work from this research project was recently published, which is a nice accomplishment for a doctoral student. So I'll cede the floor to Christian to tell you about his work.
Right, thank you very much, Keith. So, like Keith hinted at, this is some work that I did as part of my first year project. And this is work that was done with my advisor, Keith Weber, who just introduced me. So the topic of this talk is relating mathematicians' pedagogical goals and orientations to some common teaching practices in advanced mathematics lectures. And I should say that when I talk about advanced mathematics classes in this talk, what I'm referring to are college level proof-based courses that are offered to math majors. A proof you might remember from high school geometry, it's just a sequence of statements that logically establish the truth of a proposition. And these advanced math, these proof-based courses are usually offered to mostly math majors starting in their second or third year, and they make up the bulk of the math major. So the motivation for engaging in this research, so we know that math education researchers have generally agreed upon some preferred principles for effective teaching. So to put it a little briefly, this includes instructional techniques like using active learning in the classroom, and also using other techniques that are student-centered, where the mathematical concepts and arguments and discussion are mostly generated by the students and also led by the students. So this comes from a kind of constructivist epistemological stance, and it avoids a traditional transmission model of teaching and learning, where the teacher kind of passes on knowledge to the student just kind of through speaking. And actually, besides just having these preferences, there's a strong dislike for lecturing in the math ed community. It's by no means universal, but it does exist. And I have some quotes here to show you just how strong these sentiments sometimes are. So Laron and Davidsky say that teaching in which you're telling students about mathematical processes, objects, and relations is not sufficient to induce meaningful learning. Hence the sorry state of affairs, even with the best of lecturers. Helmos, in a speech he gave, also made several strong comments. He said, the best way to learn is to do. The worst way to teach is to talk. In the middle here, a good lecture is usually systematic, complete, precise, and dull. It is a bad teaching instrument. And at the end, the lecture is an instrument of last resort for good teaching. So a lot of math education researchers aren't unclear at all about their opinions about lecturing. The thing is, there's a disconnect between the research and the practice in this case, because despite all this research literature on teaching effectiveness, mathematicians still mostly lecture. And we know this from a few different things. We know that there's been several large-scale studies that have established this fact. But maybe more convincingly, there was a survey done by Bukaba Connolly and his colleagues in 2016. And they conducted a survey of 131 instructors in a course called Abstract Algebra. And so this is a specific advanced math course. And the reason that they chose to survey instructors for this course is because math ed researchers have created an inquiry-based learning curriculum for this course. And inquiry-based learning is one of these kinds of teaching methods that uses student-centered instruction, where students are really exploring and discovering theorems on their own rather than being given them by the teacher. So they did a survey of abstract algebra instructors, and what they found is that most of these instructors lecture. Very few of them are using this inquiry-oriented curriculum that math education researchers have developed, and very few are using math education research at all as a guide for the teaching. Instead, they seem to be relying on their own experiences as teachers, but also their own experiences as students, and to a lesser extent, conversations that they have with their colleagues about teaching. Another thing this survey showed was that mathematicians lecture because they think it's effective. But what the survey doesn't tell us is why mathematicians feel this way. And this is something that Fukawa Connolly and his colleagues acknowledged. They called to understand the rationales that instructors have for using lecture to teach. And this is a call that's been put forth by several math ed researchers in the past as well. So the study I'm going to talk about today is an attempt to see how we can understand mathematicians' motivations for using lecture in light of all this research. And maybe more importantly, this study also explores how knowledge of these motivations can help us inform research we do in math ed, especially around how we can change instruction in advanced math classes. Oh, sorry, I think I skipped. And so before I get into the study, it's important to know a little bit about the research literature on what lecturing looks like in advanced math classes. And so based on some large scale studies, we do know of some commonalities that these advanced math lectures share. And I'm going to present 3 of them to you today. These are the 3 that are germane to our talk and to our study. So the first is due to Artemeva and Fox in 2011. So these researchers, they weren't actually math education researchers, but they investigated 33 college level math classes across 7 countries in the world. And their goal was to see what kind of similarities they would find and differences. But one of the striking similarities they noticed was that in every single one of these classes that they observed, the instructors were using something that they call chalk talk. And chalk talk consists of 3 main components. So the first component, probably pretty obviously, is that the instructor is writing mathematics at the blackboard, the chalkboard. Secondly, they're not just writing. As they're writing, they're narrating what they're writing, and also possibly what they're thinking as they're writing. And thirdly, chalk talk doesn't mean that the instructor always has to be at the chalkboard. They may pause occasionally and face the class and offer what these authors call a broader meta commentary on how the mathematics that they're presenting fits into some larger framework. So the second study that's important here is due to Fukawa Connolly and actually Keith and Pablo here at the GSE in 2017. And this is on how lecturers in advanced math classes present formal and informal mathematical content. So these researchers, they defined formal mathematical content to be these exact kind of things like definitions, theorems, or proofs. And they considered informal mathematical content to be heuristics for solving problems, heuristics for proof writing, informal representations of mathematical objects, or maybe informal ways of thinking about the math. And what they found about the way that lecturers in advanced math presented this kind of content was that when these lecturers were presenting formal content, so when they presented definitions, theorems, or proofs, they almost always wrote that on the blackboard. There was almost never a case where they didn't. But in most cases, when these instructors were presenting informal content, they presented this exclusively orally, meaning they just said it to the class. They didn't write it on the board. Okay, and the third relevant set of teaching practices that seem to be common in advanced math lectures revolve around teacher questioning. And this is work that was done by Paoletti and his colleagues. And again, this is several at the GSE. There's at least two in the room today, Keith and Victoria. And they found that in these advanced math classes, instructors do ask a large number of questions per lecture. So they seem to ask on average 56 questions per hour and 20-minute lecture. And most of these questions, they were asking students to provide the next step in a proof, or recall a simple fact, or to do a simple calculation. And the really important one for the talk today is that when these instructors ask questions, they very frequently gave students less than 3 seconds to respond before they moved on. In the literature on questioning, this is often called wait time. So the wait time is how long you wait after asking a question before you continue. And so one of the main findings of this study was that wait times for questions in advanced math lectures are very short. Okay, and so if we're going to look at mathematicians' motivations for engaging in these common practices in lecturing, then we need to pick a good theoretical framework. And the one we settled on for this study was Schoenfeld's Resources, Orientations, and Goals framework, or the ROG framework for pedagogical decision making. And so Schoenfeld introduced this framework in 2010 as a way to explain how teachers make decisions, although he posited that this could be used to explain any kind of complex decision-making process. And so the way that Schoenfeld explained this framework is that an individual's decisions can be explained by three things. So the resources, orientations, and goals. An individual's resources are the external tools that the individual has access to, but it also includes the relevant knowledge they have in the context of the decision. So an individual's orientations are their beliefs, attitudes, and any dispositions that the individual holds in relation to that decision-making context. And their goals, which are maybe more self-explanatory, these are the aims or the ends that the individual wants to achieve by making this decision. And so it's important to say that one of the things that Schoenfeld prided himself on with this framework was that it allowed him to explain what were considered some baffling teaching decisions. So in the book where he introduced this framework, he uses the ROG framework to explain some teaching episodes. And these were episodes that included some pretty famous teachers like Deborah Ball, who was once president of the AERA, making decisions that might be described as bad, right? Considering the lesson that she was working on. But by looking at these teachers' resources, orientations, and goals, Schoenfeld was able to offer up sort of a rational explanation for why these teachers did what they did. And it's kind of for this reason that this framework is perfect for us, because we're in the same kind of scenario here, where at least from the perspective of a math education researcher, mathematicians are engaging in a baffling teaching decision, which is the decision to lecture. And if we want to take kind of an asset-based approach and say, well, let's assume that these mathematicians have some kind of rational explanation for doing what they're doing, and this might be a good framework to employ. So that's what we did. And so our official research questions for the study were, what goals do mathematicians have when they teach advanced mathematics classes? What beliefs or orientations guide mathematicians' use of these common teaching practices that we talked about a few slides ago? And what is the relationship between these common teaching practices and mathematicians' pedagogical goals and orientations? Right, so to investigate these research questions, we used semi-structured interviews. So we sent out invitations to all mathematicians at a research university who had taught a proof-based math class, an advanced math class, in the past 5 years. And 8 mathematicians agreed to participate, so we included all 8. What happened in these interviews is that we talked to the participants about 5 sets of findings from math education research studies. The only ones I want to focus on in this talk are the findings concerning chalk talk, formal and informal content, and teacher questioning in in advanced math lectures. So these are the ones that we talked about earlier. And so what happened is during these interviews, we would hand the participants a summary of these research findings, kind of like we talked about. And then we asked them the following questions. So we asked, to what extent do you believe these results are accurate? Do you engage in these practices, and why or why not? Are these good teaching practices? And what are the strengths and weaknesses of these practices? And so after we collected all the data and we transcribed these interviews, then we coded the transcripts. I should say we did 2 rounds of analysis. The first round of analysis is where we coded the transcripts in the style of Braun and Clark's thematic analysis. So here we were identifying common themes in the responses given by the participants. And we kind of separated these themes by the particular teaching practice the participants were talking about. So we had themes for chalk talk, themes for formal, informal content, et cetera, et cetera. And so when I talk about a theme in this presentation, it'll be contained within this box. Okay, and so that first round of analysis where we grouped the interviewees' responses based on commonalities helped us do the second round of analysis, which was the resources, orientations, and goals analysis. And so we kind of used that thematic analysis to search for goals, orientations, and resources that might help us explain why our mathematicians in our study teach how to teach. And so resources were less common in the analysis. So I'm going to focus today on goals and orientations. And so I should describe our criteria for inferring goals and orientations from the interview data. And to put it shortly, goals will correspond to course outcomes that the participants had for their classes, whereas orientations are more about features of a classroom environment that our participants felt were desirable, appropriate, or somehow useful for learning, like conducive to students' learning. And our participants could either state these goals and orientations directly, or they might state them indirectly. And when I say indirectly, what I mean is that they might evaluate a teaching practice as positive or negative because of whether or not it achieves an outcome or an orientation, or I should say satisfies an orientation. And in that case, we inferred a goal and orientation from that kind of statement. So for example, if a participant said, I think X is a weak way to teach because then you can't do Y, we would infer Y as a goal from a statement like that. Okay, and so our results included a bunch of resources and, a bunch of orientations and goals that the mathematicians in our study seem to possess. But I wanted to talk about just a few of them today. And these are a few that tell a more interesting story. And that story is that, unsurprisingly, like most mathematicians, our participants do lecture. And they lecture despite knowing some of its weaknesses, right? And these are weaknesses that math ed researchers have talked about for a while. But the thing is, we've also figured out some of the goals that our participants have that are served by lecturing in the way that they do, right? And so I'm going to present some of those today. And thirdly, even though these mathematicians do lecture, they seem to have an orientation that might serve as a bridge between the way math education researchers would like these advanced math classes to be taught, and the kinds of things that mathematicians, at least the mathematicians in our study, value. So I'll talk about all three of these today. Okay, so for the simple part, it does appear our participants lecture. 7 of the 8 participants that we talked to agreed that they use chalk talk, at least to some extent, in their advanced math classes. But at the same time, another 7 of the 8 participants agreed that lecturing is not engaging for students, right? So this is something that math education researchers would also say. And this came up in a theme that we call chalk talk does not engage students, so rather straightforwardly. So next to the theme, I'm going to present some quotations that help to illustrate it. And so here we have a mathematician who I'll call M5. M5 was speaking about the weaknesses of Chalk Talk, and they said, well, I would say, as described there, I think lack of student involvement, students as passive agents. So that was a weakness they found with Chalk Talk. M7 says, obviously, this particular activity that's listed here, referring to Chalk Talk, doesn't involve any sort of interaction. So these are all things that most math education researchers would agree with. Right? But the fact remains that despite most of our participants saying these things, most of our participants still use Chalk Talk in lecturing. And so that remains to be explained. And so that's what I hope to do to some extent in this next part of the talk. Right, so what are the participants' reasons for engaging in lecturing and in these lecturing practices that seem to be so common? So what I'm going to do here is present some of the goals that we found in our ROG analysis that at least the participants perceived were served by the practices that we discussed earlier. And so I should say everything I'm talking about here are perceptions of our participants. And it might sound like I'm stating something as fact, but just keep in mind that these are the perceptions of the participants. Okay, and so we're going to talk about these goals based on the practices that the mathematicians perceived to achieve them. And so we'll start with the practice of Chalk Talk. And one of the goals that our participants perceived Chalk Talk to accomplish was covering material in the course curriculum. And so we inferred this goal from one theme in particular, which was Chalk Talk provides control over the structure of lessons. So in this theme, the comments that contributed to this theme, I should say, participants really talked about how Chalk Talk allowed them control over aspects of the course, like the pace of the course, the material that they were covering, and even the mathematical notation and language that will be used in the course by the instructor and the students. So to illustrate here, M1 said, I think that anything else that you try to do instead of Chalk Talk is a lot more painful and hard to control the speed of the course. So if you have, for example, a given amount of material that you want to get through in one semester, you can't get bogged down and spend the entire semester on the first week's worth of material, even if it might be very interesting. So another goal that our participants believed to be served by Chalk Talk was teaching students a mathematical way of thinking. And we saw this mostly in the theme, Chalk Talk models mathematical thinking. And so what the comments in this theme talked about were that teaching is about helping students develop a mathematical mindset. And that the instructors had this kind of thinking framework, this mathematical thinking framework, that probably most of the students in the class don't yet have. And Chalk Talk allows the instructor to display their mathematical thinking framework to students who hopefully can pick up on it. So we have M2 illustrating this theme. M2 said, I do believe that modeling is really important. That is, the instructor should be doing what the students are going to be expected to do, and modeling that in real time, rather than relying on a text to be the model of, this is how you write the math, this is how you actually write the mathematics. I'm just going to give you the big picture, and here's how you actually do the details. That modeling, thinking about the details in real time, is important. So I think that is a good thing about the old-fashioned way that we work. And I should point out here that M2, by saying the old-fashioned way that we work, is referring to Chalk Talk. This comment was made in that portion of the interview. And actually, M2 is connecting the idea of modeling a thinking framework to two parts of Chalk Talk. So two components of Chalk Talk. The first is the component of writing mathematics on the board. And we see that when M2 talks about this is how you actually write the mathematics. And the second is the narration piece of Chalk Talk, where the instructor is narrating their thinking. And M2 kind of emphasizes this when they say thinking about the details in real time is important. And it's also important to note out, to point out that M2 says that really you can't rely on the text to do this, that it really is a Chalk Talk that's helping them do this. Okay, one last goal associated with Chalk Talk here is the goal of preparing students to be mathematicians. And we saw this actually in a few themes. One of them being Chalk Talk is tradition, and the other Chalk Talk is complicated by heterogeneous student abilities. And I'll talk about each of these themes. So in Chalk Talk is tradition, comments were about how Chalk Talk's really a longstanding part of math culture. And the participants talked about how they themselves experienced Chalk Talk as students. And also that Chalk Talk has been successful at producing math and at producing the mathematicians who create that math. Here M6 kind of illustrates this. They say, so is a blackboard, referring to Chalk Talk. I mean, is that good practice? I think it's a good practice in the sense that a whole lot of math has happened in the last 200 years. And this is how it was disseminated. So it historically has worked fantastically well. The theme of Chalk Talk is complicated by heterogeneous student abilities. This was different. In this theme, participants were talking about how when you use Chalk Talk, you're writing one thing on the board that's being seen by many students. And these students might be at different places, right? So they might have completed different courses before this point, and they might have a different comfort level with the content that's been presented in the course up to now, right? So even though you have all these different kinds of students in the class, you're writing one thing on the blackboard, and they might be getting different things from it. But here in this comment that's part of this theme, M4 speaks particularly to this goal of preparing future mathematicians. So M4 says, maybe about 10% of math majors would go, maybe about 10% of math majors would then go on to try to become research mathematicians. And they're the ones who would primarily benefit from these upper level math courses. The other ones, they'll get through it. They'll learn a little bit of something, but in some sense, it will be incorrect to tailor the experience for them because they're not the ones who are going to be using it later on. So here, M4 is really talking about how he deals with this complication of having students at different levels in the classroom. And the way that M4 deals with it is by defaulting to the students who will become research mathematicians, right? They go as far to say that it will be incorrect to tailor the experience for the other students. Okay, so we see the goal of covering course material again, but this time related to the practice of giving short wait times for questions. And here again, we have a straightforward theme connecting this practice and this goal. And that's the theme: instructors give short wait times because they have to cover material. And of course, the gist of this theme is that instructors give short wait times because the longer you wait for answers to questions that you ask, the less time you have to cover content. M3 illustrates this here. I think there's a good reason why instructors don't wait. It's because they've got material to cover. And it's almost always a race to cover a certain amount of material in a lecture. And this sort of thing can take up a lot of time. If you ask students questions and you wait for them to actually digest the material enough to be able to answer a question, it's very time consuming. Okay, so to recap this part of the talk, we saw a few goals that the participants in our study perceived to be served by lecturing, and especially these particular lecturing practices. So those goals were covering material in the course curriculum, and we saw that our participants were able to, or believe they were able to achieve this through Chalk Talk, because that gave them control over the class structure, and through giving short wait times to questions so that they would have more time to cover content. We inferred the goal of teaching students a mathematical way of thinking, and instructors believe to get this through by modeling their own thinking framework as they narrated their thinking in Chalk Talk. And lastly, the goal of preparing future mathematicians. And our participants perceive this to be achieved by Chalk Talk because of the historical success of Chalk Talk in producing mathematics and mathematicians. Okay, so we know that our participants lectured despite its weaknesses, and we saw what goals they believed these lecturing practices would accomplish for them. But we also have something in our study that suggests that we might find a source of agreement between math education researchers and our participants, at least. And this we actually saw earlier. So you'll recall that 7 of our 8 participants said that one of the weaknesses of Chalk Talk was that it doesn't engage students during class. And I also said that one of the criteria we used for inferring orientations from these comments was if instructors, or I should say if participants, evaluated the teaching practice negatively because it didn't create a certain classroom environment. And so that's exactly what we have here. And so we see this orientation of engaging students during class time that might be shared by both our mathematicians and math education researchers. And we didn't just see this orientation expressed here. We actually saw this orientation connected with teaching practices that our participants talked about. So that's what I'll go into now. And so we'll see how this orientation aligns with some of the things that mathematicians in our study said they do. And so the first thing that this orientation of engaging students during class seemed to align with was this practice of presenting informal mathematical content exclusively orally and not writing it on the board. And so the theme where we saw this arise the most was a theme called oral presentation is needed to hold students' attention. And you might guess what kind of comments appear in here. One of them from M3 says, well, in my experience, when the instructor maybe puts down the chalk and turns to the front of the class and addresses the class with some anecdote or some informal way of thinking about a concept, as is written here, that's when students start paying attention. A lot of them will just be kind of phased out, blanked out. But when you turn around to talk to them, they suddenly start paying attention. So I think it's very important to do this informal talking. And other participants that contributed to this theme talked about the way that oral presentation sort of helped students focus. Okay, another practice that this orientation of engaging students during class, so ways that our participants believe this align with their practices, was in asking many questions. And so a theme, again, another straightforward theme where they showed up a lot was questions help to actively engage students. And this was a really popular theme. So 7 of our 8 participants made comments that contributed to this theme. And M3 here describes it very well. They say, I mean, asking questions is very important because it engages the students, wakes them up from falling asleep. If you ask them questions, it also draws attention to what's important. It jogs their memory. And it creates an atmosphere of paying attention, how important it is to pay attention. So in this scene, mathematicians really talked about how asking questions can help the students get thinking and get them engaged in lecture, right? By paying attention, by thinking, and by, I guess sometimes keeping them awake. Okay, so to summarize, we saw that our participants, like most mathematicians, are engaging in lecturing in their advanced math classes. And they're doing this despite what the research literature says, and despite the weaknesses they see with their own eyes. But we also saw that the mathematicians have goals that they feel are served by these lectures. Right? So we saw the goal of covering course content, the goal of teaching students an authentic mathematical thinking framework, and of preparing future mathematicians. I'll point out that in our paper, we discussed some other goals and orientations that I don't have time to talk about here. But if you're interested in those, you can look at the paper that Colleen attached to the email announcing this brown bag. So besides just the goals that we saw these mathematicians in our study profess, we also saw some orientations that might be promising for math education researchers if they want to change instruction in advanced math classes. And this orientation was that students should be engaged during class. And I say this is a promising orientation because this is something that math education researchers agree with. And we actually see that the mathematicians in our study believe that some of their practices that they were doing were kind of, were contributing to this orientation, right? They were contributing to student engagement. And so we see that the mathematicians here do value this. And if they do value this, then that's something that might be a good leveraging point for instructional change. Oh, and I want to point out, the paper contains a lot more orientations that I didn't talk about today. And I think some of them are really interesting too. So there's this orientation of being precise when presenting math that I found personally interesting. And there's also a really relatable orientation of avoiding awkward silences in the classroom. So you can read about those in the paper as well. Okay, so I mentioned that this study only had 8 participants, and so we can't really generalize the orientations and goals that we found for our participants in the study to mathematicians at large. That wasn't the point of this study. But we still believe that it has some contributions to make to math education research, particularly in the way that math ed researchers go about effecting instructional change. And the first of these is that while these orientations and goals might not generalize, they at least provide a plausible starting point for examining the goals and orientations of mathematicians at a larger scale, right? So these goals and orientations that we found might form a good base for surveys that could generalize to a larger population. And I'll point out that some of the goals that we found are almost certainly, they almost certainly generalize, right? So the goal of covering course material is one that's been talked about widely in the literature. But there are some goals that we have which are kind of understudied. So for example, the goal of preparing future mathematicians is one that seems to slip the radar of math education researchers, right? Which would make sense because math education researchers, of course, are focusing on math education, so they might not think about this idea of producing mathematicians as much as mathematicians might. But if this is a goal that generalizes to mathematicians at large, then it's something that will be important to know, right? And that kind of takes me to the next point here, which is that it's important to consider the pedagogical goals and orientations of mathematicians when math ed researchers are creating instructional interventions, but also when they're convincing mathematicians to adopt these instructional changes. And there's a few things to be said here, which is that in some cases, the interventions that math ed researchers come up with might actually align with mathematicians' goals, right? So for example, if the goal of preparing future mathematicians generalizes, right? If this is a goal that many mathematicians have for their courses, and if it's the case that this inquiry-based learning curriculum that was developed for abstract algebra courses, if it's the case that this curriculum still produces a large number of PhDs in math, and these PhDs in math go on to do good research, then this is something that might be hardening to mathematicians, right? That might be useful in convincing them to adopt this instructional intervention. However, there's going to be cases where the instructional interventions just don't align with mathematicians' goals or orientations, right? And in this case, it might just be necessary to exert some effort trying to persuade mathematicians to change these goals and orientations if we feel that they're not conducive to good teaching. And of course, that's easier said than done. But that leads to a third point, which is that graduate student teachers or graduate students in general may have more malleable pedagogical goals and orientations than mathematicians do, right? So if convincing mathematicians to change their goals and orientations after, in some cases, decades of teaching, if that seems like an intractable problem, then maybe this last thing isn't, right? And it should be noted that there is math education research that's been done where researchers investigate the beliefs of graduate student teachers and teaching assistants. But as far as we know, there hasn't been work done where orientations and goals are explicitly addressed in teaching training, right? So it might be important to address things. So for example, one of the orientations that came up that I didn't get a chance to talk about today was teaching how you've been taught. Right? And if math ed researchers believe that teaching in the way that you've been taught isn't the best orientation to hold, maybe they'd rather these graduate student teachers adopt the orientation to be open-minded about teaching and to teach in the ways that are effective, even if that means trying new things, right? This could be something that's addressed more explicitly in teacher training. Okay, and the last point I want to make is that as the survey by Fukawa Connolly and his colleagues kind of showed, mathematicians aren't adopting these large-scale reforms, like the IVL curriculum for abstract algebra. And these reforms right, so one of the things that we talked about was covering course material, and I didn't mention this before, but this IBL curriculum developed by math ed researchers for abstract algebra, this cuts out a lot of content, right? And so from the goals that we saw in this talk, this might just be too much against the goals of the mathematicians for them to adopt this curriculum as it is. But at the same time, we saw in the third part of this talk that the mathematicians were implementing small practices that they felt helped them engage students in the class, right? And so if this does generalize, then this is something that mathematicians value, then it might be the case that we can get smaller lecture compatible interventions into these advanced math classes that sort of promote active learning among students, and which mathematicians will actually be more prone and more willing to adopt. And Dawkins and Weber talk about this in a 2020 paper, and they offer as examples clickers that could be used in the classroom for answering questions, and the idea of partial notes. So these are kind of notes with main bullet points hit for students, so that they can focus on writing down sort of big ideas and not focus on getting verbatim what the instructor says or writes on the blackboard into their notes. So these smaller interventions might still be compatible with the kinds of teaching that math education researchers would like to see in math classes, while at the same time being compatible with the orientations and goals of mathematicians. Okay, and that's all I have for the talk. I have here some thank yous to the people that made this research possible and made this talk possible. And thank you for listening.
Thanks, Christian. We'll open it up for questions. You can raise your hand, use the chat. I saw a couple of comments. Oh, go ahead.
So I can ask some.
Yeah.
I have a couple of questions. I'll ask one. So I'm wondering, I mean, it seems like I was intrigued by the modeling mathematical thinking assumption that well, it's a goal, but the assumption that in modeling mathematical thinking, your students are actually learning that and attending to what it is that you're modeling. And I'm wondering to what extent these faculty thought that, in fact, the students were getting what they thought they were getting out of this, right? So if your goal is to model mathematical thinking and sort of the procedural strategic ways in which you develop these explanations or proofs or what have you, do they have any evidence, or do they really think that the students in their class who are busy copying from the board are getting that?
Right. And so, yeah, I think you've hit on a point, which is that just because the participants are saying it doesn't necessarily make it true. We're not endorsing that, or we're just looking at what they're saying. And it does seem to make this assumption that this is effective. I have some other quotes that might I'm trying to see if I have it in this slide here. I do. Okay. Oh no. All right, I don't. Well, there was another participant that said that really the only way to get students thinking like this, the only way to intervene with their thinking to get them into a more mathematical mindset is by exposing them to it. So I think that this was kind of at least for some of the participants, a strongly held belief, right? There was also this belief from M2 that you don't want to rely on the textbook to do this. You need to be narrating it and talk about the thinking as these details are being written down. So I believe that these mathematicians felt that there was this importance in the narration in modeling the mathematical thinking. They also kind of talked about this in this section of the interview about informal content. Oh darn, I don't have that here either. But what they said is that a lot of times in the formal mathematical content, like definitions, theorems, and proofs, the way that stuff is produced, like the motivation behind it, the way to arrive at the insights that might go into a proof, or even a definition, that's kind of stripped out of the way that you present them when you write them down, even at the blackboard. And so they said part of the importance of that informal content is conveying those ideas. And that might be something that they feel is important for them to do by telling it to the students. But again, this is all based on their perceptions, not necessarily like research-based.
Right. Yeah, I get that you're not saying that you agree that is the best way that the students are actually getting it. But I think that the assumption that by modeling, they're actually, my guess, and I don't know, is that the students are writing everything that's on the board and probably missing a good chunk of all the extra justifications that, and I don't know how much of that they're actually writing, whether they're just listening and whether it's even, whether they are understanding the epistemic goal behind the why I'm verbalizing what I'm doing, which I just think that's interesting.
Yeah, I mean, that's also another part of this this research, is that the study that was done by Fukawa Connolly and Keith and Pablo, one of the really striking findings is that students almost never wrote down what instructors were saying, only orally. So if it didn't go on the blackboard, it didn't make it into their notes. And when it made it into their notes, it was almost verbatim what was written on the blackboard. And so, yeah, I think you're right here that, I mean, and this might be another way to get instructional change through, is to kind of challenge these ideas that mathematicians have. Say, okay, you have this goal and you think it might be achieved by chalk talk, but here's this other result that suggests that might not be the case. So I think that's a good point, yeah.
Christian, there's a question in the chat from Brittany. No, it's okay. That's what I'm here for. She wasn't sure if you answered this, but did you share the information with the math department here at Rutgers or any research school? And if so, what were their responses?
No, I haven't yet shared it with the math department. That would be something interesting to see. I guess I would kind of provide sort of like a member check to this stuff. But yeah, maybe I should schedule that. I guess I can reach out to some people there. But yeah, thanks for that idea.
I have a comment or two if no one else does. First of all, thanks for this talk. It's really interesting and I think very important work to understand the thinking of mathematicians who are lecturing and using the chalk talk methods. I guess my comment comes from my own experience in teaching advanced math courses. I'm thinking of 3 courses in particular: the abstract algebra course, which is undergraduate course, the Mathematical Theory of Probability course, and an applied mathematics course at the graduate level for engineering students. And the abstract algebra course is a proof-based course, and the other two might be called more problem-based courses, in that the emphasis isn't on rigorous proofs, but on techniques of solving math problems. And where I think a lot of what you're saying applies to the problem-based courses as well, even though you were focusing on the proof-based courses. And also my experience is one of having moved from in my much earlier career, using basically exclusively chalk and talk methods, to coming to understand through work in education that this wasn't very effective, and trying to modify those methods, and running into the practical considerations that function as constraints to trying to do that modification. One of them is class size. I found it much easier to introduce inquiry-based methods in smaller classes than in large, what might be called lecture size classes of more than 20 or 25 students. And second is the expectations of students themselves, particularly in the graduate course in engineering, which had about 50% students from abroad and 50% students from the United States. The expectation of the students was very clearly that they wanted to see example problems and worked solutions by me. And my expectations were that I wanted to see them understanding the thinking behind the problems they were addressing. And that meant a much more inquiry-based approach to it. So that difficulty of meeting student expectations was rather strong at that level. So I just wanted to make those comments that these are really interesting points. I think the math department here would be very open, at least many people would be open to looking at this, because I've been part of discussions of lower level courses in mathematics, the pre-calculus and calculus sequences that where there's been a lot of advocacy for a more inquiry-based approach. And this is, of course, very difficult in these very large lecture courses. The upper undergraduate courses tend to be a little smaller and may be easier to implement this kind of approach. So do you have any ideas about these things?
Yeah, the first thing you said actually was brought up before when I presented this work, that there's probably all this stuff might be true for most math courses, at least most advanced math courses. And that's possibly the case. But I think since a lot of the practices that like the research we're basing this on was contextualized in advanced math classes, I think it's probably important to keep it there. For all we know, like I try to tell the participants, like we sort of talk to them, okay, how many proof-based courses have you taught recently? And this study was about proof-based courses. For all I know, they were drawing on experience from other advanced math classes. There's not really a way I can control for that strictly. But I think you're right, it probably does apply to lots of math classes. And the second thing, sorry, could you remind me what the second comment was
The
about?
second thing is the constraints that
Okay.
make it difficult to make the change, even when someone is very highly motivated to do that.
Right. And so from the design of this study, we were talking to the mathematicians about the results, which kind of were describing, not kind of, they were describing teaching practices as they are. And so probably not by bringing up the idea of changing instruction, those kinds of constraints might not have been foremost on their mind. So for example, we didn't really see much about class size in the interview data, which might have come up if we particularly talked about introducing IBL into a classroom. But we did, I think you're right, we did see participants talking about students' expectations for sure. One of these was in an orientation to be precise. So some of the participants talked about how if you write something on the blackboard, students might expect that it's all worked out, that it's exact. And so if you're presenting an informal idea, which probably, unlike theorems, has exceptions or has nuances that are really difficult to express formally, then you don't want to give them this false impression. And that might contribute to why these instructors are only saying it orally, not writing it down. So they are thinking, I believe, of student expectations a lot. We just didn't see it in kind of the things you're describing because of the design of the study, I think.
Mhm. I think sometimes a person might be thinking about why they do something, and tacitly, one of the reasons is if they kind of imagine doing it a little differently, they imagine it being hard, and so they don't go down that path. So then they start looking for the positive reasons why to continue doing it, rather than that kind of tacit awareness that it would be hard to do because some constraints might exist.
Right.
But anyway, I think this is great. Thank you for presenting all this. And I hope you do take it a little further into the question of what would be involved in, what do mathematicians think might be involved in shifting.
Thank you.
I think we have time for one more if anyone has anything else. Okay, I guess we'll end on that note. Thank you, Christian, again for presenting. Next week is our last brown bag of the semester, so be sure to join us. Okay, have a good afternoon, everyone.
Thanks, everyone.